so yesterday or in the last lecture, we have covered up to this point. We are going through the problem of design of singly reinforced section, and this is the problem. Okay, we will take quick review of the problem. The problem was design a beam of effective span 6 meter and the total working load was 12 kN per meter including the self weight. The width of beam is limited to 250 mm. Width is given to you and M20 Fe415. So we have assumed width of support as 230 mm. We have calculated the depth. We consider the L by D ratio as 10, and after that we calculate the overall depth, effective depth. Then we calculate the factored load. After that we have gone for bending moment calculations. Then we take the check for depth. After that we have calculated the steel. We have provided two bars of 16 mm diameter, okay, at bottom, and at top we have provided two bars of 10 mm diameter. These bars are not designed for bending moment, but these bars are provided for anchorage to anchor the stirrups and by the norms of the earthquake ice code. So after that we have done check for shear. We have calculated the shear force WL by 2. From that we have after the shear force calculation we have calculated nominal shear stress tau v VU upon BD. After that percentage of steel at support we have calculated. The percentage of steel at support is the percentage of steel at center divided by 2. So from that we got the percentage of steel at support. Then from this percentage of steel we have calculated allowable shear stress. Okay, so the allowable shear stress we have calculated based on this. So now after that that allowable shear stress comes out to be 0.28 Newton per mm square. This is the allowable shear stress. Now then shear resisted by concrete, we have calculated what the shear force can be resisted by the concrete. So to calculate the force, again the basic formula is stress into area. So allowable stress is 0.28. So this stress we can allow. uh, After the value exceeding this stress is not allowed. So we have taken the maximum stress into the area. So we have calculated the shear force 42 kilonewton. We got the shear resisted by concrete. So out of 54 kilonewton, 42 kilonewton is resisted by the concrete. Then the remaining unbalanced shear force is 12 kilonewton. So for this 12 kilonewton, we have designed the shear reinforcement. Okay, we have provided two-legged 8 mm 5 stirrups. The area of stirrups is the area of stirrups is we have calculated 100 point this 53. This is the area of the stirrups. After that we have calculated the spacing of the stirrups. The spacing of stirrups is calculated by these three criteria. Okay, so the spacing of stirrups is first 0.87 fy asvd upon vus. Then after that 0.87 fy asv upon zero point 0.4 bu, zero point 0.4 b, sorry, and then in no case the spacing shall be taken as 300 mm. So list of these three values we should consider. So the list of these three values is 300 mm. So we have provided two-legged 8 mm 5 stirrups about 300 mm center to center. This is the overview of the problem. Now after the shear calculation we are going to check the development length. So LD, what is the formula for LD? Development length. How to calculate development length? It is phi sigma s upon, it is 4 tau bd. Okay, tau bd is a single term. So 5 sigma s upon 4 tau bd. This is the formula to calculate the development length. So the development length can be calculated as phi is 16 diameter. Sigma s is again 0.87 into fy. This is the value of sigma s whole divided by 4 tau bd. 4 into value of tau bd is 1.2 for M20. Okay, and it should be increased by 60% when the reinforcement is provided in the tension zone. So it is 1.6. Now if you calculate further, then the development length will be, it is 16 into 0.87 into 415 whole divided by 4 into 1.2 into 1.6. So what is the answer? LD
752.18.
752.18. This is your development length. Now calculate this term 1.3 m1 upon vu plus L0. This we need to calculate. Okay, so therefore, what is the value of m1 now? M1 is equal to, it is, we always take it is mu by 2. So what was the value of mu? What was the value of mu? What we have calculated? I think 81 kilonewton meter. This is the value of mu. So here you put the value 81 divided by 2. What is the answer? 40.5. Am I right? The answer is 40.5 kilonewton meter. So it is 40.5 kilonewton meter. This is your M1. Now VU, shear force. What was our shear force? VU is the shear force. So we have to take the shear force. So what was the shear force? Let me know the value of the shear force. What we have calculated? What is the shear force?
54.
54. 54 is the value of shear force. Okay. So the shear force is 54 kilonewton. This is our shear force. Then the value of L0. How to calculate the L0? It is width of support. It is width of support divided by 2 minus clear cover. Width of support divided by 2 minus clear cover. This is the L0. Okay. So to calculate L0, L0 is equal to, what is the width of support we have assumed? It is 230 divided by 2 minus our clear cover is, what clear cover we have assumed? 20, 30, 25, I think 30. 30. So solve this. What is the value of L0? 230 by 2 minus 30.
85.
85. So L0 is 85. Now put all these values into the equation so that we will get this value. So put all these values. So it is 1.3. It is 1.3 into M1 is 40.5 into 10 raised to 6. Okay, divided by VU 54 into 10 raised to 3 plus L0 is 85. What is the answer? Let me know the answer.
85.97.
85.97.
97.
It is correct answer, 85.97.
Sir, 0 0
Huh?
1060.
1060 na?
Hmm.
Okay. This is the correct answer, 1060. So this is not correct. So answer is 1060 mm. Okay. So as usual, our LD is less than 1.3 m1 upon vu plus L0. Okay. Hence it is safe. Hence it is safe. Okay. Hence it is safe. So now we have taken the check for shear as well as check for development length. There is no need to take the check for deflection in the case of the beams. Okay, because our moment is proportional to the beams and we we always given that width and depth ratio L by D is equal to 10. That automatically satisfies the deflection criteria. So now after this, what we need to do, we have to draw the reinforcement details. Okay, so for the reinforcement details now, I will draw here the cross section. Okay, so here is the cross section of the beam. Of 10 mm diameter are at the top, and at bottom 2 bars of 16 mm. So here reinforcement is provided in this way. These are the 16 mm diameter bars which I have shown over here, and now these are the 10 mm diameter bars which shown at the top side. This is the 2 bars of 10 mm diameter, and now we will show the stirrup. Okay, so we have to draw the stirrups. The stirrups may be like this. Okay, to hold these bars, you draw the diagram correctly. Okay, so this is the stirrup I have drawn over here. Okay, so this is the hook somewhere here. So this is the bar of 10 mm diameter. Here are the bars, and the remaining these two bars are of 16 mm diameter. Show it correctly. Okay, give the names. This is 2 bars of 16 mm diameter, and these are the two bars. These are 2 bars of 10 mm diameter, and here this is the stirrup. Okay, so two-legged. What was the diameter? 8 mm or 10 mm? Stirrups diameter? It is 8 mm. 8 mm, 8 mm stirrups, two-legged, 8 mm stirrups, 8 mm diameter stirrups, about 300 mm center to center. Okay, about 300 mm center to center, and the dimensions are, this dimension is 250. Okay, what was this total dimension? Effective depth is 602. What was our what we can say overall depth? What we have calculated overall depth? So the overall depth 250 by 640 is the section size. Okay, so this depth is 640 mm. From this point here to up to this point 640 mm, and up to the center of this bar. Okay, the depth is 602 up to the center of this bar. So this is the typical cross section of the singly reinforced beam what we have designed now. Okay, I hope it is clear to you. Draw the diagram. Shall we move ahead?
Yes, sir.
Okay, so now we will take the next problem. So here in this problem, if you see, a problem is very easy. Just you have to go by step, and just you have to check that whether the checks are satisfied or not. Okay, so in this problem, if the only condition is that here they have given working load of 12 kilonewton including self weight, but sometimes in the numerical they don't give the sentence like this including self weight. They only tell you that the working load of 12 kilonewton per meter is acting on the beam. just this may be the sentence. In that case, you need to add this self weight of the beam separately to that load. So we will take that type of problem is also one more that type of problem. Now we will go to the next problem. So write down the next problem simultaneously with me. This is our question number how much? Fourth, five, sixth. This is our question number. I think what was this? Fourth, five. So the problem number five. So now we will take the next problem. Problem number five. Okay. The problem number five. In this problem now, we will take one numerical. A singly reinforced beam. Take the problem. A singly reinforced beam. A singly reinforced beam. 250 mm by 500 mm. 250 mm by 500 mm is reinforced with is reinforced with is reinforced with 4 bars of 16 mm diameter. 4 bars of 16 mm diameter. Okay. 4 bars of 16 mm diameter with effective cover of 50 mm. With effective cover of 50 mm. Okay, so effective cover is given 50 mm. So effective span of beam is 6 meter. Effective span of beam is 6 meter. Effective span of beam is 6 meter. Okay, so here now what they have told further, use M20 and Fe250. Use M20 and Fe250 to determine the central concentrated load. To determine the central concentrated load okay, that can be carried by the beam. That can be carried by the beam. Okay, by the beam in addition to its self weight. In addition to its self weight. Okay, so other than its self weight, one concentrated point load is acting on the beam, and you need to calculate what is the value of this point load or concentrated load. Okay, so I will read the problem once again for clear understanding. A singly reinforced beam 250 mm by 500 mm is reinforced with 4 bars of 16 mm diameter. Reinforcement is provided given to you. The effective cover of 50 mm. So directly they have provided you effective cover instead of clear cover. Okay. Effective span of beam is 6 meter. Use M20 and Fe250 to determine the central concentrated load that can be carried by the beam in addition to its self weight. So M20 is also given, Fe250 is also given, and we need to determine the concentrated load that can be carried by the beam. So to solve these types of problems, first we need to calculate what is the moment mu. Okay, so we need to calculate the bending moment mu. So the formula for bending moment mu is tu into z or cu into z. Okay, so either of this we can use tu into z or cu into z. To decide which formula we need to use, we should calculate that the given section is under reinforced section or balanced section or over reinforced section. To compare that the given section is under reinforced or balanced or over reinforced, we need to calculate the value of xu and the value of xu max. Okay, so from this we can calculate the concentrated point fluid. Okay, so first of all, we will write the given data. So what is given? So B is given to us, width of the section. So B is given to us, it is B is 250 mm. Okay, so B is given to us, it is 250 mm. Then overall depth, it is 500 mm. Then effective cover is given to us 50 mm. So our effective depth will be D is equal to overall depth minus effective cover. Effective cover is considering the half of bar diameter. Whenever you come the word across effective cover, clear cover means half of bar diameter is not covered in that. And effective cover means what? It is by considering half of bar diameter. So 500 minus 50, it is 450 mm. This is the effective depth. So then FCK, FY, these values are also given to you. FCK is equal to, what is the value? 20 Newton per mm square, and the value of Fy is 250 Newton per mm square or 250 MPa megapascal, one and the same thing. So AST, area of steel, is given to you. So area of steel, AST, 4 bars of 16 mm diameter. So 4 into pi by 4 into 16 square. What is the answer? Let me know the answer.
804.24.
804.24 mm square. This is the area of steel. Okay, now calculate XU. Okay, so to calculate XU, we equate CU equal to TU. Okay, to calculate XU, we are assuming the balance section and equate compressive force is equal to tensile force. Equate CU equal to TU. Therefore, what is CU now? The CU is 0.36. It is 0.36 FCK B into XU, which is equal to 0.87 Fy into AST. So therefore, just put the values. 0.36 into FCK, FCK is 20, into B, width of section, it is 250, XU, XU as it is, which is equal to 0.87. Okay, 0.87 into Fy, Fy is 250, and AST. Okay, what is the area of steel? Area of steel is 804.24. So if you do this calculation, you will get the value of XU.
97.17.
So the value of XU is 97.17 mm. This is the depth of neutral axis. Now calculate maximum depth of neutral axis. Okay, calculate maximum XU. Okay, so XU max. So now XU max is equal to, what will be the XU max for Fe250? So it is 0.53 into D. So this is for Fe250 grade. Okay, this is given on page number 70 in the IS code. Okay, it is given in the page number 70, on the page number 70 in the IS code. So XU max is equal to XU max is equal to 0.53 multiplied by D is into D. D is, what is the value of D? D is 450. Okay, so the value of D is 450. So from this, you will get the value of XU max.
238.5.
What is the value?
238.5.
Okay, so it is 238.5 mm. So who is less and who is greater now? So XU is less than XU max. Okay, if XU is less than XU max, then which type of section it is? If XU is less than XU max, okay, then this type of section is nothing but it is under reinforced section. This is under reinforced section. Okay, so this type of section is under reinforced section. So in the under reinforced section, how do you calculate MU? So in the under reinforced section, to calculate MU, we use the formula. Okay, now to calculate MU, that is moment. To calculate moment or bending moment, you can say. Calculate moment. MU is equal to, it is TU into Z. It is TU into Z. So MU is equal to, what is TU? It is 0.87 Fy, then AST into, what is Z? Z is D minus 0.42 XU. 0.42 XU. So now MU is equal to, now what is the value of MU? So just put all the values. MU is equal to, it is 0.87 into Fy. Fy is 250 into AST, it is 804.2 something into D, that is your effective depth, it is 450 minus 0.42 into XU. What was the value of XU? It is 97.17. So if you solve this, you will get the value of MU.
Sir, 71.57
71.57 kilonewton meter.
trillion.
Okay, so this is the value of mu. Now we got the value of mu. Now this is the total bending moment which is acting on that beam. Okay, this is the total bending moment which is acting on that beam. Now if you see the beam, if I draw over here the beam, then it will be, okay, so now so this is simply supported beam. This carries UDL, that is dead load. This UDL is nothing but dead load. Okay, so dead load comprises of self weight of the beam, dead load. And in addition to this dead load, the beam carries a point load at the center. So here it is the point load P. We don't know what is the value of this P. Okay, but it is acting at the center. If this total span is 6 meter, then this will be 3 meter. As this total span from this point here to the last point, it is given as 6 meter. As this total span is 6 meter. Okay, so this dead load is nothing but self weight of the beam now. Okay, and not any other UDL is not acting on the beam. Just they have given that we need to calculate the concentrated load, determine the concentrated central concentrated load that can be carried by the beam in addition to its self weight. Okay. So self-weight is as it is, and this is the additional load which is carried by the beam. So now, first of all, we need to calculate what is the dead load of the beam. Okay, what is the dead load of the beam? So for that, we calculate self-weight of beam, self-weight of beam, that is dead load, which is equal to, now what is the self-weight of the beam? What is its width? It is 250 into its overall depth is 500, so it is 0.5 multiplied by density of concrete 25. So if you solve, you will get the value of self-weight. Self-weight of beam. What is the self-weight?
2.12.
3.12 is 3.12 kilonewton per meter. This is the self-weight of the beam. Okay, now calculate the ultimate. So dead load is 3.12. So calculate ultimate load, ultimate dead load. Okay, so ultimate or factored dead load. Ultimate dead load is equal to what? It is 1.5 multiplied by 3.12. So you will get the ultimate load. What is the answer?
4.68. 68.
4.68. So it is 4.68 kilonewton
Yeah.
per meter. Okay. So this is our dead load W. This is our dead load W, and this is the concentrated load P. Now what is the total ultimate bending moment? How to calculate? What is the formula for bending moment in this type of condition when a beam is carrying UDL as well as a central point load? So the total bending moment in this case, we get bending moment is equal to, for UDL the bending moment is WL square by 8, plus for point load which is acting anywhere on the beam, it is PAB divided by L. PAB by L. So this bending moment value, this is known to us. It is 71.57. So I will just put the value. This is 71.57 into 10 to the power 6, which is equal to WL square by W is nothing but our ultimate dead load. This value what we have calculated, 4.68. So it is 4.68 into L square. L is nothing but span. Okay, the span of beam is 6 meters. So it is 6 square divided by 8 plus P, we don't know the value, concentrated load as it is AB. So A is 3, B is also 3 divided by L. L is 6. Okay. A is 3 and B is 3 we get from here, this point. So this distance, this is nothing but your A this side, this distance is nothing but B, and this total length is L if this is P. So now, so A is 3 meter and B is also 3 meter as it is acting on the center. So if you put these values and if you solve this, you will get the value of P. Huh,
Sir, 33.67.
33.67. So the answer is 33.67 kilonewton. All of you are getting the same answer. Just check it, 33.67. 33.67. Okay. So now this is the problem for to calculate the point load. Okay. So this is the problem to calculate the point load. We have seen same problem for calculation of UDL also. Okay, how to calculate the UDL, and that safe UDL we have also calculated. Here further, if they told you calculate safe point load, okay, here they have just told you determine the concentrated load. Further, if they told you to calculate the safe point load or safe concentrated load, then you need to divide this value by 1.5. Okay, remember this. If they have asked you for the safe concentrated load. So I hope you understand this problem also. Now we will move forward to the next example. So the next is our problem number 6. Okay. So this is the design, one more design problem we will take. So design a beam of of effective span of effective span 6.2 meter, which supports a working load of 10 kilonewton per meter, which supports a working load of 10 kilonewton per meter. Okay. The width of beam, the width of beam is limited. The width of beam is limited to 230 mm. 230 mm. Use M20 and Fe415. Use M20 and Fe415. So this is the given problem. Okay. So I will read the problem once again. So design a beam of effective span 6.2 meter which supports a working load of 10 kilonewton per meter. The width of beam is limited to 230 mm. Use M20 and Fe415. So here in this problem, if they don't give you the width, suppose in this problem the width of beam is not given, they have told you it is limited to 230 mm. But if it is not given, then you just assume the width of beam as 230 mm. Okay, whenever the width of beam is not given, you need to assume the width. Normally it is 230, 250, 300, but 230 is the standard value. So now after this, now we need to design this beam. Okay, so for designing this beam, first we will write down the given data, what is given to us. So b is equal to 250 mm. Then what they have given, span. So L effective span is given to us, it is equal to 6.2 meter, which is equal to 6200 mm. This is the effective span. Then after that, what they have given us the load W. It is 10 kilonewton per meter. This is the given load W. Then after that, what is given? FCK. FCK is equal to 20 Newton per mm square, and Fy is equal to 415 Newton per mm square. Fy is equal to 415 Newton per mm square. Okay. So now what we are going to do over here. So first of all, we need to calculate the depth of the beam. So to calculate the depth of the beam, what we do? What we do to calculate the depth? To calculate the depth of the beam, Okay, so here I have written B equal to 250 mm, but actually it is given in the problem B is equal to 230 mm. Correct. So here I should do that correction. Here 230. So B is 230 mm. Correct. Okay. So after this we calculate the depth. So here I can write depth calculation. Depth calculation. So it is L by D ratio. We will take this as a 10. Okay, so our L is 6200 divided by 10, which is equal to D. Therefore, what is the value of D now? It is 620 mm. Okay, so D is 620 mm. So now assume 16 mm bar diameter or 12 mm, whatever you want, you can assume. So we are going to assume here 16 mm bar diameter. Assume 16 mm bar diameter and 30 mm clear cover. And 30 mm clear cover. So capital D is equal to, what is the value of capital D then? It is 620 small d plus 30 plus clear cover is 30 plus 16 by 2. So which is equal to 6. What is the answer?
Sir, 658.
So it is 658 exactly. So it is 658 mm. So we round this depth to 660 mm. So if we increase our overall depth, our effective depth is also going to be increased. So to calculate the effective depth, small d is equal to, it is 660 minus 30 minus 16 by 2. What is the answer?
Sir, 622.
So it is 622 mm. Okay. So this is the answer 622 mm. So after the depth calculation, what we do next? Once the depth is calculated, what we are going to do next? We are going to calculate the load. We are going to see the load. What is the load coming on the structure? So the W is given to us. Okay, so load. So W is equal to, what is the value of W now? W is given as 10 kilonewton per meter. So calculate the factored load. Okay, WU, ultimate load or factored load. It is 1.5 multiplied by 10, which is equal to 15 kilonewton per meter. 15 kilonewton per meter. This is the WU. Okay. So now after the calculation, now load is known to us. Now span is also known to us. The effective span is directly given in the problem, 6.2 meter. So from this we can calculate the bending moment. Okay. So calculate the bending moment. Here I will write bending moment calculation. Bending moment calculation. Okay, so to calculate the bending moment, what is the formula now? So mu is equal to bending moment is equal to It is WL square divided by 8. So which is equal to, what is W? W is 15 into L square. L is 6.2 square whole divided by 8. Now what is the value of mu?
7.
72.07.
What is value?
72.07.
72.07 kilonewton meter. This is the value of mu. Now what we do after the calculation of bending moment? Always after the calculation of bending moment we always take check for depth. So we always take the check for depth. So to take the check for depth, what do? We equate the maximum bending moment to moment of resistance. So here equate your bending moment to moment of resistance. Okay. So your bending moment, what is the value? Just we have calculated the value of bending moment. The value of moment is 72.07. So it is 72.07 into 10 raised to 6, which is equal to MR. Now how to calculate the MR? How we will get the value of this MR? Fe415 is given. So it is 0.138 FCK BD square. So here D is nothing but our required depth. So I can write again 72.07 into 10 raised to 6 is equal to 0.138 into FCK. The value of FCK is 20 into B. The value of B is 230 into D. So I will write as it is D required square. So therefore from this D required is equal to, what is the required depth? What is the value of required depth? It is
336.94, sir.
okay,
6.94.
so it is 336.94, 6.94 mm. This is the required depth. And what is the depth we have provided? We have provided the effective depth as, I think so, where it is, 622 mm. So it is far more safe and uneconomical also. But okay from exam point of view. So D provided is greater than D required. Hence it is safe. Hence it is safe. Okay. So after the check for depth, what is our next step? What we always do? We go for steel calculation. Okay. Steel calculations. We go for steel calculations. Now to calculate the steel, we know the formula. So to calculate the steel, we know the formula. AST is equal to, what is the formula? 0.5 FCK BD divided by FY in bracket 1 minus under root 1 minus 4.6 mu upon FCK BD square. So we need to put the value here. So AST is equal to 0.5 into FCK is 20 into B. Value of B is 230 into value of D is 622 whole divided by Fy is 415. Here in the bracket 1 minus under root 1 minus 4.6 into mu. So what is the value of mu? It's 72.07. So the mu is 72.07 into 10 raised to 6 to 10 raised to 6 and whole divided by FCK BD square. FCK is 20, B is 230 and D square. So here it is multiplied by 622 square. So complete the bracket. So what is the value of AST? Okay, so it is 337.62 mm square. This is the area of steel. Okay. Now we have assumed 16 mm bar diameter. Now calculate number of bars. So number of bars is equal to 337.62 divided by area of single bar 5 by 4 into 16 square. Please do check the calculations, whatever answers we are taking over here. I don't have the answers. All these are unsolved problems. So for number of bars, how many number of bars are there?
1.68.
1.68. So nearly we round this value to two numbers. So we are going to provide the two bars. Okay, so calculate the AST provided. AST provided. So AST provided will be 2 into 5 by 4 into 16 square. What is provided area of steel? Area of steel.
40.
40.
402.
Exactly 402. Hmm.
Point 12.
One,
Point 1
two.
2. Okay. So this is the area of steel which we have provided. Okay. Now from this calculate the percentage of steel. Percentage of steel PT. It is 100 into AST provided divided by BD, which is equal to 100 into AST provided 402.12 whole divided by B into D. B is 230 into D is 622. Answer
0.28.
0.28%. Okay, so finally we will write over here provide two bars of 16 diameter at bottom and two bars of 10 diameter at top. This is our reinforcement what we are providing. bars at top and bottom. Hmm. After this, what is our next step? What is the next step? Next is check for shear or shear reinforcement. We need to see it is required or not required. Correct. So check for shear. We need to calculate the check for shear. Hmm. So let me know. First of all, we need to calculate the shear force. Correct. So the shear force Vu is equal to, how do we calculate Vu? Is WL upon 2, where W is the ultimate load and L is the effective span. So W, what is the value of W? What is the value of W? W is 15, correct? W is 15. So here, I think one thing is missed from us. Have you point out that thing? Can you guess what is the remain? Anybody? One thing is left us. We have not considered one thing that we must consider. Okay. So here if you see the problem carefully, what they have told us, design a beam of effective span 6.2 meter which supports a working load of 10 kilonewton and the width of beam is well. This working load, they have not given that this working load consisting of the dead load or including the self weight of the beam. So we need to consider the self weight of the beam separately, and that self weight we have not considered over here. Okay, are you getting my point? So we need to consider that self weight also. Voice is not clear. Now you are getting my voice. Everybody is getting my voice. Voice is clear or what? Yes, no. Anybody can reply me. Are you getting my voice clearly?
Yes,
Okay.
sir.
So what I am trying to tell you that, see here we have considered this 15 kilonewton per meter load, it is correct. But this load is not including the dead load of the beam. So here we forgot to take the dead load of the beam. That is what I want to tell you. Here we forgot to take the dead load of the beam. So we have to take that dead load. So you do weight of beam. Sulfate of beam means what? Dead load. You do this correction. Sulfate of beam. So what is the sulfate? So we have finalized the dimension of the beam. Our overall depth is 660 and our width is 230. So it will be 0.23 into 0.65 multiplied by 25. So what is the value? Dead load. What is the value?
3.795.
3.795. Okay, kilonewton per meter. Now calculate factored load. So multiply this value by 1.5. So 1.5 into 3.795. What is the answer?
5.69.
5.69 kilonewton per meter. Now get the total load. So add these two values. So total load is equal to, so the total load which is equal to 15 plus this 6 sorry 5.69, 15 plus this 5 20.69. What is the total value? It is 20.69. Correct? 20.69 kilonewton per meter. So here we should use this 20.69 to calculate the bending moment and all the calculations. So here write this. Instead of this you should write here 20.69 and let me know the value of bending moment again. What is the value?
99.41.
99.21. This is the bending moment. Now keep this value here also. So this value is 99.21. Okay. So the value is 99.21. 99.21. Now from this you will get the D required. What is the value of D required?
395.73.
395.73. Okay, so still our D provided is very much greater than the D required, so it is safe. But here now 395, so this answer is correct. Here also you need to change the value 72.07. Instead of that you need to put this value 99.21 in steel calculation. So take that value here also. So now you will get the value of this AST.
Sorry, AST
So it is
475.7.
475.7. This is AST. Now calculate number of bars. This calculation will also get changed. Calculate number of bars. Then AST provided. So here it is 475.7. How many number of bars?
2.36.
2.36 means 3 numbers. Okay. So the number of bars are 2.36. So it is 2.36. So it is 3 number of bars. So here AST provided is 3 into pi by 4 into 16 square. So what is the AST provided now?
603.18.
603.18. Now also put this value over here and calculate the percentage of steel.
Point 42%.
Okay, so it is 0.42%. So 0.42%. Okay. So how many bars we are going to provide now? 3 bars. Okay, so instead of 2, make here 3. Instead of 2, make here 3. 3 bars we are now going to provide. 3 bars and 2 bars at the top. Okay. So have you got the thing what we have missed? Okay, आपण काय मिस केलं होतं हे लक्षात आलं का तुमच्या? हिअर इन द प्रॉब्लेम दे सेड दॅट वर्किंग लोड ऑफ 10 किलोन्यूटन पर मीटर. आपण केलेलं हे सगळं करेक्ट असलं असतं कधी, जर त्यांनी पुढे जर म्हणलं असतं की दिस लोड इज इन्क्लुडिंग द सेल्फ वेट ऑफ द बीम और इन्क्लुडिंग द डेड लोड, असं जर त्यांनी दिलं असतं तर दिस द कॅल्क्युलेशन वॉट एव्हर वी हॅड डन अर्लियर इट वॉज करेक्ट. But in the problem what they have mentioned, they have given that the working load is 10 kilonewton per meter, that's it. They have not considered that this working load is by considering the self weight of the beam. So here as nothing is mentioned, we have to consider the self weight of the beam separately. So what we have done, this is the load, then this is ultimate load, this is given load, then self weight of the beam we have calculated, then ultimate self weight of the beam, that is ultimate dead load, and we have added these two loads to get the total load. Okay, so this is the only change in the step. If they have not mentioned you, if it is not included, then you have to do this additional thing, you have to calculate the weight separately. Okay, so now after this bending moment calculation we have done, check for depth we have taken, then steel calculation is done. By these are our regular steps. Now we will come to the check for shear. So now to take the check for shear, what is our total load? It is 20.69 into 6.2 is the L effective divided by 2. So if you solve this you will get the value of VU.
Sir, 64.139.
64.139. This is the value of VU. Okay, now calculate nominal shear stress tau v. Okay, so calculate nominal shear stress. So nominal shear stress is tau v is equal to is vu upon vd. So vu is equal to 64.139 into 10 to the power 3. Okay, vu upon bd, b is 230 and d is 622. What is the answer?
0.448.
0.448 Newton per mm square. Okay, so this is the nominal shear stress. So I can say 0.45 Newton per mm square. This is the nominal stress which is developed in the beam. So this is the stress which is developed in the beam. Now we need to calculate allowable shear stress. Okay, so allowable shear stress, allowable or permissible shear stress, that is tau c, which is equal to. Okay. So this shear stress we are going to calculate from the IS code, the percentage of steel. Okay, so the percentage of steel at center it is 0.42. So what is the percentage of steel at support? Percentage of steel at support, what is the value? Percentage of steel at support, it is half of percentage of steel at center, 0.42 divided by 2, so it is 0.21%. So we'll look up for the value of 0.21% because shear force is always exist at the support. So we will go to the IS code. Now IS code, okay, so in the IS code, this is the table, design shear strength of concrete. So now what is our value? Our value is 0.21. Here for 0.15 M20 grade of concrete, the value is 0.28. Okay, so here I will write for 0.15. What is the value? 0.15, the value is 0.28. Okay, then here for 0.25, for 0.25, what is the value? Value is 0.36. 0.36. Now we want it for 0.29, 0.21, sorry. So for 0.21 you should calculate the value. For 0.21 you should calculate the value, do the interpolation and calculate. Hmm? Take the difference between these two, take the difference between these two. Hmm? What is the answer?
0.328.
0.328. So I will consider this as a 0.33. Okay. So 0.33 we will take it as. For 0.21 the value is 0.33. So we will go to our calculations now. 0.33 we will take. Now we will go to our problem. Okay, so this value works out to be 0.33 Newton per mm square, 0.33 ampere Newton per mm square. Now here again you will see that your tau v, that is nominal shear stress, is greater than your permissible shear stress. Correct? It is greater than your permissible shear stress. So here I can write tau v is greater than tau c. So what does it indicate? Shear reinforcement is required. Shear reinforcement is required. So the shear reinforcement is required. So now we need to calculate the shear reinforcement. Okay. So we have to design the shear reinforcement. So we will calculate now. We know the total shear force. What is total shear force? It is 64.139. Now we will calculate what is the shear force resisted by concrete. Okay. So we will calculate shear resisted बाय कॉन्क्रीट. ह्याच्यातलं कॉन्क्रीट किती रेजिस्ट करू शकते ते पहिल्यांदा आपण कॅल्क्युलेट करून घेऊ. शियर रेजिस्टेड बाय कॉन्क्रीट. सो इट इज कॅल्क्युलेटेड ॲज, इट इज नोटेशन VUC. दिस इज शियर रेजिस्टेड बाय कॉन्क्रीट. इट इज इक्वल टू tau c into B into D. So now shear resisted by concrete, it is VUC is equal to tau CBD. Tau C is 0.33. Tau C is nothing but stress and B into D is nothing but area. So stress into area, we will get the force. Shear resisted by concrete. So 0.33 into B is 230 into this D is 622. So shear resisted by concrete. What is the value? What is the value now?
47.2
47.2 kilonewton. Okay. So now the developed shear force is 64.139, and out of that 47.2 is resisted by the concrete itself. So whatever may be the remaining shear force, for that shear force we need to provide the shear reinforcement. ओके, 64 किलो न्यूटन एवढा शिअर फोर्स तिथे जनरेट होतोय, त्यातला 47 किलो न्यूटन एवढा कॉन्क्रीटच रेजिस्ट करू शकतोय. मग राहिलेला जो काही शिअर फोर्स असेल तेवढ्यासाठीच आपल्याला रिन्फोर्समेंट डिझाईन करायची आहे. ओके, सो नाव द अनबॅलन्स शिअर, so I will write here unbalanced shear. Unbalanced shear, that is VUS, is equal to total shear force VU minus shear resisted by concrete. So unbalanced shear force is equal to 64.139 minus, this is 47.2. What is the answer?
16.93.
16.93 kilonewton. This is the answer. This is the unbalanced shear force. Okay. So now we are providing two-legged stirrups. Okay. So here I will write, to resist this shear force, provide two-legged, okay, 8 mm or 10 mm, whatever diameter you want, you can choose. 8 mm diameter stirrups. Okay. Now from that I will calculate the area of stirrup. So area of stirrup is 2 into pi by 4 into 8 square. What is the area of stirrup? What is the area?
100.53.
100.53 mm square. This is the area. Now we will calculate the spacing. So spacing of stirrup. Okay, spacing of stirrups. Now how to calculate the spacing? First, what we do? SV is equal to 0.87 Fy ASVD divided by VUS, unbalanced shear force. So put the values. And let me know the answer. It is 0.87 into Fy is 415, ASPD is 100.53 into DT is 622, whole divided by VUS, that is unbalanced shear force, 16.93. So it is 16.93 into 10 to the power 3. So the spacing is equal to, what is the answer?
1333.51.
1333. एवढं जास्त आहे का आन्सर? चेक करा बरं अजून एकदा.
हाँ सर पॉइंट.
Check the answer once again and let me know the answer once again. So it is 133 का?
हाँ 1.
Okay. So it is 1333.51
Five
Five
one.
one. Okay, so it is 1,333.51 mm. Okay, so now this spacing is very much high, so we are not going to use this spacing. Second criteria, SV is equal to, how to calculate the spacing? It is 0.87 FY ASV. Just remove this D and VUS ASV, and here you should write 0.4 B. So which is equal to, now tell me the answer. 0.87 into FY is 415, ASV 100 point किती 53, whole divided by 0.4 into B is 230, and in no case spacing should
394.52.
394.52 mm. Okay, and in no case it is taken as 300 mm center to center. So this spacing is nearly about 390 mm center to center. Okay, and the above spacing, if we round up, it is nearly about 1300 mm center to center. Okay, so we will take this final. In no case the spacing should be 300 mm center to center. So here we will provide two-legged 8 mm diameter stirrups about 300 mm center to center. Okay, so here we will provide that about 300 mm center to center. So this is the details of shear reinforcement. Now after the shear reinforcement, we should take the check for development length. Okay, so next is the check for development length. Check for development length. Okay, so the check for development length, we will calculate the development length. LD is equal to, it is phi sigma s upon 4 tau BD. So just put the values, you know these quantities. So sigma is 16 into, sorry, phi is 16 into sigma is 0.87 into 415 divided by 4 into tau BD value is 1.2. And when it is provided in tension zone, then increase it by 60%. So the development length is equal to, what is the value of development length now?
752.18.
752.18 mm. Now calculate the value of m1 first. M1 is equal to what? It is mu by 2. So what was the value of our mu? It is 99.21, I think so. Divided by 2. What is the answer? What is the answer?
49.6.
Okay, 49.6 kilonewton meter. This is M1 VU. What was our total shear force? It is 64.13 kilonewton. Okay. So put the value 1.3 M1 upon VU. Okay. So M1 upon VU plus L0. So you need to calculate L0 also. So first of all calculate L0. किती येते L0? L0 is equal to width of support by 2 minus clear cover. So we have not taken the width of support. So assume width of support as 230 mm divided by 2 minus clear cover as 30 mm. Okay. For your understanding, you show the arrow here and write down assumed width of support. So now from this, what is the value of L0 now?
85.
85. So put all the values in the formula. 1.3 m1 upon vu plus L0. So it is equal to 1.3 into the value of m1 is 49.6 into 10 raised to 6. Okay, divided by vu 64.13 into 10 raised to 3 plus 85. Let me know the answer.
Sir,
So
1090.45.
it is 1090.45. So our LD is less than this quantity, hence it is safe. So here we can write LD is less than 1.3 m1 upon vu plus L0. Hence it is safe. Okay. Now I will draw here a rectangle. It is a rectangular section. We will show 3 bars of 16 mm diameter. So this is one bar, is second bar, this is our third bar. These 3 bars are of 16 mm diameter, and at the top there are 2 bars of 10 mm diameter. This one bar is of 10 mm, this another bar is also 10 mm. Okay, so I will name them. This is the 2 bars of 10 mm diameter. If you see, these are the 3 bars of 16 mm diameter. Okay. And now we will draw the stirrup. So if I draw the stirrup, so now here if you draw the stirrup, it will be like this. Holding the bars. Okay, so this is our stirrup, 2-legged, 8 mm diameter. So and the dimensions are, this is 250, and this total depth what we have calculated, 660. This is 660. This total is 660. This 250. This is your reinforcement details. Okay, so these are your reinforcement details. So today now, is it over? Yes or no?
Yes.
So for today we will stop here. In the next lecture we will see the numericals on doubly reinforced sections. Okay, so B is equal to 230. In the reinforcement diagram right now which I have shown there I have written by mistake b equal to 250. Okay, it is not 250, it is 230. B is 230 and your overall depth is 660. Okay, so by mistake if I written there 250, you correct it, you write there 230 by 660. Okay, so now in the next lecture we will start with the design and the concepts of doubly reinforced section. Okay, so we will meet in the next lecture now.